repeat it. Okay. So, okay, this is what I want to do because the embedding projector is taking long to load. On a slow network, it actually takes a bit of time. So what I'll do is, if you remember, I just explained that in the embedding space, right? If you were to plot things that are similar, they will tend to be bunched together. And if you were to even this in a three-dimensional space, you look at this plot. What this is in a two-dimensional space. So I'm going to do an example, and I'm going to use the PCA, which we did last time, to reduce the dimension of the buildings to just two dimensions, and I'll plot it in a two-dimensional space. And then we will see what the similarity looks like. So that's what I'll do while we are waiting for this embedding projector to load for us to see it. Okay. Um, and I was also saying that this is the method that you can use to plot to get embeddings. You can use this sentence transformer. Um, and I'll explain this in more detail later on, but this is the method I'm going to use. So let's go into it. So the first thing is we will get sentence transformer in Colab. Sentence transformer is already installed, so you don't need to pip install it or anything, right? You just import it. So from sentence transformer is provided by Hugging Face, right? Hugging Face provides a lot of different embedding models. An embedding model is a model that's been trained on any kind of modality, whether it's text, image, or anything like that, right? So that after being trained to predict things with images, that last prediction layer is removed, and you are left with a layer where it has meaning. That's what we call the embedding layer. And if you remember, that's kind of what I was trying to show here. Um, if we want to talk about how embedding models are made, basically embedding models are made by taking a neural network. We'll talk about that when we get to neural network. You train it, you train it on data to predict, but it's not a prediction you actually want it to learn. After it has learned the entire meaning, you remove a few layers, um, you know, that it uses for prediction, and it will be left with layers that basically hold the internal meaning. So if you go to Hugging Face, you can go to huggingface.co. You see there are a lot of models here, and you just go to the models um, sub sub um, site, the part of the site that you have. You see a lot of different things here. So you have libraries, you have transformers, and you have sentence transformers. So typically, if you go to sentence transformers are basically transformers that are trained to be embedding models. So effectively, you can use them for your embeddings. Okay. So that's how you can get one of them. So the one we are going to use right now is this sentence transformers all mini LM L6. You can take any of these other ones, especially anyone that has embedding, on it. It's more likely going to be. You can even see it has sentence similarity here, sentence similarity, sentence similarity. So these are models that are trained to be able to generate embeddings from which you can calculate similarity between words and sentences. Okay. I can just copy this, right? It's actually difficult to copy, but if you click on the word, you'll see a copy icon here where you can copy this to copy the name of the model. So we are going to use that name of the model later on, but let me just paste it somewhere for now. So I paste it here. So there are two things you do. I just want to get embeddings from this. So to get embeddings, there is a sentence transformers package, which on pip, you can install it if you're doing locally, or on your local notebook. But if you're doing it on a Colab notebook, then you don't really need to install it. It just comes pre-installed on Colab. Well, that's one of the benefits of using Colab. Okay, so this will take a bit of time because it will have to start the runtime. But after this, I will create a new instance of the model, right? So the instance of the model I want to create an instance of this all mini LM. So to do that, I will do model equals sentence transformer. So basically sentence transformer using the class that I had imported. And then I pass in the name. Okay, well, it has already guessed it, so I don't need to do this. So it pass in the name, all right, all mini LM L6V2. That's the model. And it's as simple as that. So this model, of course, it's going to download it from this sentence transformers are not API calls. It downloads it locally into your computer. So um, this one is pretty quick because this is a very small model. It's not that large. It will give you an embedding of length 384 dimensions, 384 features. So for you to use it, it's very simple, right? You just do embedding equals model dot encode. You just use the encode method, and then you pass the text, right? Which can be any text, or it can be a word, it can be a sentence. So let's say like you want to get the embedding for dog. That's it. You've gotten the embedding for dog. If I print it, this embedding is normally returned in the form of a NumPy ND array. Okay. So if you look at it, you can see it is just a list of numbers, floating point numbers, minus 5.314659834, E minus O2. I hope you know what E minus O2 means. E means exponent. That is not exponent as in the exponential function, but exponent as in 10 times 10 raised to power minus 2. So this is basically divided by 100. So if you divide this by 100, it gives you a 0.05. So the actual value of this is 0.053, right? So you can see that these are embeddings, these are values, the value of this particular thing called dog or concept in different directions. Okay. Um, you could also do the same. By the way, I want to show you the shape. If you want to check the shape will tell you the dimensions, the size of the dimensions. And you see that it's 384. I can now do another embedding. So let me call this just dog. So that's a dog embedding. Okay. Now we can also do a cat embedding, which is you encode the word cat again, and you are going to get an embedding for cat. You can also still print that, and you can see again, it's a very long list, a long array that contains 384 floating point numbers that represent the meaning of cat to this particular model. That's what the word cat means to this particular model. And if you check the dimensions as well, you see that the shape is again 384. Now we could do something and say, okay, let's print the two of them. So I could let me just print the two of them. Let me see if I use print if it's better. And I print cat and then I print dog. So it's going to give me the two of them. Okay, one thing I think we can do, um, it prints the two, but it's too much for me to see. So let me see if I can reshape it. np.array. So I am now combining the two of them. Um, I'm now combining the cat and the dog to form a composite ND array. And I need to import numpy first, of course. Import numpy. as NP. Okay, so it's still giving me the two, but I now want to um well, one way, okay, let me use a different approach. Um let me just use a different approach. So let me just take the first 10 numbers or the first five numbers in the list. Cats, let's take the first five numbers in the cat list, so up to five. And then the first in the dog as well. So up to the first five in the dog. So we'll now see the two of them together. It's not as much as before. Um, I could also just do it as a tuple. I want something that is easy to see so you can see the two. Okay, so you can see now that the cat, the numbers that represent the cat, the first five numbers of 380 something, right? 0.037, 0.05, minus 0.003, and so on. And this is dog. We could also do the same for a car. So let's do for a car. So car is now the interesting thing with this thing is that if you say okay, let me go and check the let me just go and see whether I'll find some um some of these features that are close together. It might be a bit difficult because but already you have already seen that this, for example, this second one, okay, the cat and the dog are close together. This is 0.05, 0.01, but the cat has a much higher value, 0.1. Okay, so you can even tell that this is a dimension or this is a feature that kind of differentiates them. It might not be the only one, it might not be the perfect one. This one doesn't differentiate because the values are very close to. In fact, in this one, the cat is closer to the car is negative, the dog is negative, right? But the cat has this, and so on. So you can do this, but this is not a very good way of comparing the similarity, right? So now, where you can do some kind of similarity comparison is, let's say we use principal component analysis, PCA, like we did last time. So import from sklearn um, covariance. I think it's covariance. Yeah. So from sklearn you import PCA. Okay. So okay, this is for calculating. So this is I got the wrong thing. It's not from covariance. Um, I need to find where it is. Um, yeah, this is cosine similarity, but I'm not trying to calculate cosine similarity right now. Sklearn dot. Okay, I use the wrong word. It's actually still from covariance, but it is principal. Okay, it's from decomposition. Yeah, sometimes I mix this up. So import PCA. Okay, so we'll get PCA from decomposition. Right. So we get decomposition, we get PCA. Uh, we will now take these three I will put the three of them into a single um, array. So remember, these three are three different vectors. So we'll take the three vectors, I'll put them into a single vector, right? So we can say embeddings. You could we could actually have combined the three of them, um, but but that's okay. I think let me do it the best way um we would do it. So words, right? The words. Let's say we have three words. We have cat. We have okay. Let's start with a dog. We have dog. We have cat, and we have cat. So we take these three words and we put them into the embedding model. We encode it. So the other interesting thing you see that for Hugging Face embedding models, you can also pass a list of words, and it's going to give you embeddings for all the words, right? So this embeddings is now going to give you, if you check the shape, you now see it's 384 by 3 or 3 by 384. That is, there are three words, right? And the embedding size of each of them is 384. Okay. So that makes it very convenient. You don't need to have to do one by one or one at a time. Okay. Now, we could also just look at the embeddings themselves to see how they look like. So you see the three of them are there. Again, take note that the numbers are exactly the same. They didn't change. That's why I said that for the same words, you have exactly the same embeddings. No, the numbers never change because there's a determinism to it. It's deterministic. All right. Of course, it would be wrong if they were not the same because that would mean that the meaning can change, right? But here, so we have dog first, then we have cat, then we have car. Okay, now the next thing I want to do is I'll do a PCA. We could do a when we did principal component analysis last time, we did a scalar. We used standard scalar to do scaling, but we're not going to scale here because scaling it will change the meanings, right? And these words are already in the range of 0 to 1. So you don't need to scale anything. You just go with what you have. But if you do scale now, you're going to change the meaning, and that will be very bad. So we will keep it and we'll just do a PCA, right? So we can do a PCA and we'll specify the number of components, right? Um, well, there are 386, 384 features, right? But let's just reduce it to maybe like 20, even though I will not use all 20, but so that it'll be faster, I'll reduce it to 20. So I create a PCA and then I will then transform the embeddings. So you could say embeddings that have been passed through PCA, principal component analysis. So remember what we said, principal component analysis is going to um, basically shift the embeddings into a space and extract the principal components from each of them. Okay. So this will give me embeddings. Okay, the number of components must be between 0 and the minimum of number of samples, number of features. So I only have 3 samples. That means I cannot do PCA. Oh yeah, that's true. PCA algorithm, we can't do dimensions that have more than the number of samples. And I have 3 samples, just the three, dog, cat, car, or number of embeddings. So let's just make this a three components, so it will fit. So I now have that. I can then print the embeddings now after. So take note that this PCA thing I'm doing is just for me to be able to plot it, right? It is not, it does not have anything to do with the meaning. PCA changes the meaning of embeddings, right? But its only purpose is for visualization or other kinds of analysis, right? So you can see with this PC has kind of extracted principal components, 3 principal components. You can already see that this one is a large number, 0.2, right? This is 0.3, this is 0.6, while this one is to the power of 8. So this is the third component is actually quite small. So I can then take these two components and I plot them in a graph. So I'll use matplotlib. Um, okay, so I'll bring in matplotlib. I'm just going to plot the three of them as scatter plots. Um, so the best way to do it would be plot the first values against the second values. So I'll just do plot.scatter. And the first values are going to be embeddings PCA 0. I'm going to plot not the first row, rather the first column. So the first column. And then I'll plot this first column against the second column. Um, 1. The third column is basically not very it's not very significant. As you can see, the value of this third feature, the principal component, third principal component is very small. So I'll plot this without too much this thing. It's a scatter plot. Right. So this is the scatter plot. So the only thing is I don't know which is which. So let's put in some colors. And I could say color equals, I could just bring in an array 0, comma 1, comma 2. Just to differentiate the colors. All right. So the first one, CMY. So cyan, magenta, yellow. So the first one is dog. That's C. The second one is cat. That's M. Then this is car. Now the interesting thing is this. I could also decide to plot only on the first um, principal dimension, right? But the interesting thing is that on this axis here, you can see that the dog, the cat are very close, right? And the car is very far away. But on this axis, they are kind of equidistant, right? Um, the car is in between, midway between dog and cat. So it might just, I don't know what this second dimension would mean, right? But in the first dimension, you can see that the dog and the cat are close together, right? But in this second dimension, the dog and the cat are opposite numbers. So it's interesting that if you look at this, right, this represents that they are both animals. So that's why they are close. While this represents what they are. So the cat is the opposite of a dog, kind of. So, um, yeah, and that's what PCA does, and other kinds of dimensionality reduction. But this allows you to see that if I now were to take this and say, okay, let's plot the y-axis. Let's plot the principal dimension, which is this. Let's plot it on the y-axis, right? And we don't plot anything on the x-axis. So the um, let's just plot um, well let's just plot only one thing. But this would now be on the x-axis. So I do need a y-axis to plot. So let's uh, we could reverse it. So let's reverse it and plot. Let's plot the other thing. I don't know what that is, right? On the x-axis while we plot whether they are animals. So you see that these are down here. If you even look at what we had, it's kind of is similar here where you see the cat and the dog are kind of vertically lined up. But on this x-axis, they are on opposite sides. So this is the animal, you could say this is the animal plane, while the car is this. But the other interesting thing I have seen here is that this is negative. So maybe this is not the animal plane, but the um, inanimate object plane, kind of. So you see that um, the car is very high, while the cat and the dog are low and they are negative. So this one indicates that cat and dog, but they are this almost the same value. So this means they're animals, while this one is non-animal. So embeddings give you an idea of meaning, and you can then take this and plot. If you plot a lot more things than just these three on a three-dimensional plane, that's what we get with this embedding projector. So let's I'm trying to reload it so we can see. So you can see it's actually using PCA to compute this. And you can zoom in, you can zoom in and you can you actually see a lot of different words. This is a cloud with a lot of different words. And you see that words that tanker, shortwave, petroleum. I don't know how, but there's a cluster right here in the middle. This uses PCA, as you can see. Then you can switch to Disney as well. Um, it also allows you to do, yeah, it's using nearest neighbors with Disney. Disney is still a nearest neighbor algorithm, but it's a more advanced one. Um, and then you can use color map. You can use color maps as well. So this is um, this is just an idea of what embeddings look like. Disney is more computationally expensive. That's why it's a bit slow. And, uh, yeah, so that's it. I'll share this link so you can take some time to look at it. So that's embeddings, right? And the principle of embeddings is basically once you have been able to extract embeddings, then similarity is just a matter of com computing or calculating the distance, right? And just that understanding that I can get words, sentences. By the way, the embeddings, you can get embeddings for entire sentences, right? Because the meaning is not just one word. Whole sentences can have meaning. We'll talk about that shortly. Then you can take that, use distance between two embeddings to calculate similarity in meaning. And that makes it very powerful. So with that, we can do search, recommender systems, RAGs, and all of that. So the interesting thing that we get from all of this is the fact that what I've just explained, that when you take a neural network, how did we arrive at this point? You take a neural network, you train it with data. Okay. We'll talk more about this when we get to neural networks, so I'm not going to dwell too much on this. You have what we call hidden layers in neural networks. And each hidden layer, you can have multiple hidden layers. Here it just shows one hidden layer. You can have a stack of um, lots of hidden layers. Each hidden layer learns increasingly useful representations of the original raw data that you have sent to it, of the meaning of the relationships in the original raw data, the relationships in the features and in the data set. Okay. And that's it. So a good example is that if you take an image classifier, for example, the input that you're passing is the pixels. Again, remember everything has to be converted to numbers. Images are represented as pixels. Those pixels are basically numbers that represent the color, intensity, and saturation and all of that. Well, we'll talk more about that later. And then the input pixels, layer one will learn the edges, layer two will learn the shapes, and layer three will learn parts of objects. The final layer can learn the entire object, right? But the important observation you find there is that the hidden layer activations become embeddings. They are embeddings. They are internal representations of the meaning of whatever you have given to the model to learn from. So like I said, embedding is simply a vector. A vector in this case is a list of floating point numbers, right? And that vector has a number of dimensions. That D, that's what we call the dimensions or the embedding dimension. So the one I just did had a 384 embedding dimension. This dimension also essentially means the number of features that embedding model has been able to learn to extract. Well, that is how it was designed. That was the architecture of it, right? So um, there are many different models today that are used. Some of these ones that you are seeing are like the older ones that were used in the old days. The Word2Vec, which has a 300 um, vector dimension or 300 embedding dimension. The Glove, which had 300 again. BERT, we'll talk about all of these when we start talking about neural networks and natural language processing. This one has 768. Then OpenAI has text embeddings as well. OpenAI's embedding models can have up to 1,536 different floating point numbers in that list. That's the embedding dimension. And then modern vision models have even more because there's a lot more information in um, pictures, in images, in videos, right? So we also have a trade-off for you to think about when you want to select what type of embedding model to use. The dimension. If you have more dimensions, like more numbers in the vectors, it's going to be more expressive, it's going to be more accurate, but also going to have more storage and it's going to require more storage, more computation. If you take a lower dimension, smaller, models, smaller dimensions, smaller embedding dimensions, it's going to be faster, it's going to be more compact, but it may not be perfectly accurate. It may lose some information. So both of them have their own uses, the higher dimension models, embedding models, and the lower dimension embedding models. So you decide how to use them, and we will talk about that. This is just a slide to talk about how embeddings work. So like I said, typically you start off with text. The text is broken into tokens. Token can be just words. So you take the text, you break it into the words and make it up. Even though in the machine learning and AI world of today, tokens are slightly smaller than words. Sometimes the words are even chopped and so on because it's now neural network models that do tokenization. Before, human beings used to do tokenization. And as a human being, the natural boundary for you to split your text would be word boundaries. But anyway, that's the first step. Then you take each of these words and you pass it through a pre-trained model that converts it to a numeric vector, which is the embedding vector that we just talked about, or the embedding, right? And these are examples. We've seen this already. And you can see the dimension is between 384, like what we just saw with the Hugging Face All Mini LM. And then it can go up to 1536 for the OpenAI text embedding vector. So the vector normally captures the context, the meaning, relationships, like we've said. So after you've done tokenization and encoding or embedding, the next is to calculate the distance. That's what we mean by vector distance. How far apart are the embeddings? Since the embeddings represent the meaning, that will also be how far apart are the meanings, right? And similarity is computed using a few metrics. We are going to look at in detail at these metrics. The first one is cosine similarity. This one just uses the cosine equation or function, basically the angular distance between the embeddings. Remember, embeddings are actually points in a multidimensional space. You want to see that way. And you can draw a line from the origin of that multidimensional space to each of those points. When you draw a line from there to that point, that is really the vector. That's what we mean by vector from a physics definition. Remember, in physics, a vector is a line that connects two points in any arbitrary space. In physics, we used to talk about three-dimensional spaces, XY, or two-dimensional spaces, XY, or three-dimensional XYZ. But when it comes to machine learning, we now talk about multi-dimensional spaces, where the dimension is essentially a number of, um, you know, features that that vector represents. So if you were to take that and plot it, then you draw a line. That line still forms a vector. So a vector can be any of those. That's why they are called vectors. They are all the same thing, right? Whether it's a line from origin to a point in space, or the numbers that represent that point in space, they all represent the same thing, that point in space. So when you calculate the angle of that point in space, or the angle between two lines that you draw from the origin to two different points in space that represent two different concepts, right? Or two different embeddings that, represent that concept. That angle is what cosine similarity is calculating. And that angle is a measure of the distance between those 2 points. That's cosine similarity. The second is the Euclidean distance. Euclidean distance is measuring the square root of the difference between the when we used to there's something we call resolution. When you take a vector in that 3D space, you have a resolution of it in the X and Y. Uh, so let's look at it this way. Let's assume I'm just going to um, I want to see if I can explain this. I've run out of time though, but um, so so typically if think of a two-dimensional space, let's not go too far. Right? In a two-dimensional space, you have a single point. Think of this as just a point in that two-dimensional space. And this point, right, has a value which is made up of the X and the Y components, right? So just think of that. Now the vector would be the line that you draw that connects the origin, which is this point, right? That point is space. This is actually the vector, right? But then the vector could also be represented by XY, because after all, the vector is just, you know, um, 0, 0 to XY. So the number XY represents a vector. And in this case, for the context of our, vector, this vector is now made up of two numbers, 0.3, let's just say, and 0.5. Those are two numbers, right? In this, so this is the embedding that represents this vector, 0.3 and 0.5, assuming that the X value is 0.3. In other words, we are assuming that the X is 0.3, right? And the Y is 0.5. So this is kind of now relating everything so that we can see that these things are all related, they're not different, right? So you have a graph, that's 0.3, and this is 0.5, right? That mark this point. It's the same thing, okay? Three different ways of representing the same thing. Now, if we're doing the cosine similarity, let's now assume I have a second vector, right? So this could be x1, y1. And then you have a second vector, a second point in space, right? In this same two-dimensional space, let's say I have a second point, and this second point is here. I can also draw, let's use a different color. So, you know, um, yeah, so, okay, so I have a second point in space, right? Representing a second embedding, a second concept, right? And that one also has its own X and Y. So I'm also going to represent its own X and Y by drawing its own X and Y. And so it has its own X, right? And has its own Y, right? And you could also say similarly that the X and Y that it represents, you can have two values here. In this case, it'd be maybe 0.4 and 0.4. So 0.4, right? And 0.4. Okay, so if I draw the lines for this second embedding or second concept or whatever you want to call it, right? This will be its own line, okay? And if I want to draw its coordinates on the X and Y axis, this is this, right? And this is this, okay? And those 2 points also represent 0.4. Okay, so this is 0.4 on the X axis. and it's also 0.4. It just happens to also be 0.4 on the y-axis. So it's also 0.4 on the y-axis. Okay, so we have this, right? So we have two embeddings. Now, we can calculate the distance between these two embeddings in different ways. That's what we are saying. The first one is a cosine similarity. This cosine similarity is actually going to calculate the distance, the angular distance between these two lines. So let me draw this as an angular distance. So the angular distance between these 2 points, right? That's the cosine similarity, basically. And the formula is going to use is going to do that. So because I'm using theta here. So that's the angle between these 2 points. That's one way. That's cosine similarity. Euclidean distance is you are now calculating the distance between these 2 points, this direct distance. And if you look at it, this direct distance is calculated using is a Pythagorean equation. By the time you simplify it, you are going to calculate the difference between x, the red x and the blue x. Let's say x, and then the difference between y, the red y and the blue y. So x0 minus x1 squared plus y0 minus y1 squared, and you take the square root of that. That's a Pythagorean equation, right? That will give you this distance here. That's the Euclidean distance. So that's another measure of similarity by measuring the distance. Dot product is a third measure. Dot product actually still arrives at this same thing, right? But you are now using a matrix function because a dot product is actually the sum of the components, right, in each dimension. So these are all different ways of doing the same thing. But at the end of the day, what you are just measuring is how far away is the red point, which represents this embedding, and the blue point, which represents this embedding. And that's how that does. So when you are using cosine similarity, typically when they are similar, the value will be 1. When they're unrelated, the value will be 0. When they're opposite, the value will be -1. That is when they are exactly the same, the value will be 1. That is cosine of 0 because cosine similarity, if they are very similar, basically they're on the same vector line. So the angle between them will be 0. So cosine of 0 is 1. That's why cosine similarity is always 1. Now, if they are not related, that means they'll be more or less perpendicular to each other. And the angle between them is 90 degrees. So cosine of 90 is 0. Okay. And if they're opposite in meaning, that means this one is on this side, while the other one is on this other side. Okay. Then the angle between them is 180 degrees, and the cosine of 180 is -1. So this is how you understand cosine similarity. Now let's look at how these are calculated. You can see it's very simple. Based on what I have explained, Euclidean distance is basically the sum of the square root of the sum of the square of the distance between the x and the y coordinates, which I just said. So for each well, you can call it data point, or for each embedding that you want to calculate the distance, it's just xi minus y. Sorry, not each embedding, not each data point, each feature. Because I just use only 2 features, right? But if you have multiple features, then each feature has an x component and a y component in a particular coordinate space that you are using. And you just calculate the difference between them, right? Let me rephrase. This is x is the first embedding and y is the second embedding. So this notation is slightly different from the notation I just used, just to avoid confusion. In the notation I just used, x and y were the coordinates in the space x and y, right, were the coordinates. But in this particular notation, right, to avoid confusion, here x refers to the first embedding, which would have features like x1, x2, x2, right? x3, x4, and so on. So please, I just want to clear that. I should probably have used the same notation to avoid confusion. While y is the second embedding. So let's assume in this case, x means the dog and y means the cat. So you are comparing the distance between the dog and the cat. Okay. Um, I just need to clarify that. So um, while in the previous one, the X was one feature in the dog and the Y was another feature in the dog. So let's to avoid confusion. So yeah, so with that, if you look at this now, then if you want to calculate distance between the X, which is, for example, the dog, and Y, which, for example, is a cat embedding, you will take the each feature, right? That's what this I means. For each of these features, you subtract the difference between them and then square that difference. And then you add the squares of the differences. So it's a sum of the squares of differences, and then you take a square root. So it's a root mean square error. It's basically a root mean square error because the error is now the difference between xi and yi, which is the difference between the two. Well, you could call it error, but root mean square difference, right? So we're already used to that, okay? So except that you're now calculating the difference between each of the features, between the two embeddings. And then you square the differences, and then you sum the square for each of the features. For all of the features, you sum the square of the differences, and you take the square root of that. That is the Euclidean distance. And that will tell you how close these two embeddings are to each other. Okay, that's the first method. It's still the same thing here. So in a two-dimensional space where you have 2 points, x1, y1, and x2. This one is using the other notation I used, where yeah, the x and the y are actually the embedding components, right? But it's still the same thing. This is now x2 minus x1 squared plus y2 minus y1. So this is using the other notation, while this one is using this notation. So I probably need to normalize the notations to avoid confusion. So in a 2D space, you have two components that you're adding, two features. In a 3D space, you have three features that you're adding. In an n-dimensional space, you have n features that you're adding. So basically the same thing as this. That's Euclidean distance. So like I said, it's the distance. While cosine similarity is actually measuring the cosine of the angle between the lines that are drawn from origin into this point. So you can see it uses this calculation. This x dot y is actually a dot product divided by the absolute value or magnitude of x times the magnitude of y. So it's essentially doing what we call a unit vector in the direction of that embedding. And like I said, if the two of them are the same, right? Um, X is the first embedding and Y is the second embedding. So if they are the same, then of course it will be one. If they are opposite, they'll be -1, and if they are not related, it will be 0. So that is that's how you measure similarity. So with that, we can then talk about the different kinds of word embeddings that we have. There are so many of them. Word2Vec, right, was one of the original ones that was used, right? And it was developed by Google Research. And that was used in the early days to train a lot of models because if you want to train models on text or natural language, you have to use embeddings to encode the words that come in. That's a feature engineering there. You have to use embeddings. You can't use maybe label encoding or one-hot encoding. That will not work. You can already see that embedding is kind of a more advanced form of one-hot encoding, except there's no one-hot, right? Every feature has a value. Unlike one-hot, where it's only one feature that has a value of 1, and the remaining features have values of zeros. So, and one of the things that they found out that was very interesting was that after training models on a lot of data, they actually began to learn these correlations. A cat and a dog will face the same direction, like what we just saw when I plotted that graph. And just without even giving these models any label data, right? On their own, they're able to extract the meaning and the context. This is another interesting thing that they did, where they found that if you actually did some mathematical operations between the embeddings, it makes some kind of sense. Like if you take the embedding for king and you subtracted the embedding for a man from the embedding for a king, you get a value. And then you add to that value the embedding for woman. The answer you get will be almost the same as the embedding for the word queen. Meaning that if you take man out of king, what will be left is something that has a meaning that is like royalty or something, right? It was able to learn that a king is kind of a sum of two separate embeddings. One is embedding for man, and the other is embedding for royalty. It kind of learned that because, in the process, it was able to classify it. So if you now take that embedding for royalty and you add it to the embedding for woman, you now get the equivalent royalty that is female, right? And that's what queen was. So the researchers discovered that these embedding vectors were able to capture a lot of things, including things like gender, things like the tense of a sentence or a word, geography, relationships, a lot of stuff. If you take the embedding for Paris and you subtract from it the embedding for France, and then you add to it the embedding for Italy, it's almost the same as the embedding for Rome. So it's able to find that if you subtract the embedding of Paris from France, you get something that means maybe a relationship that is capital of or something like that. So it was when researchers discovered these kinds of things that they realized that these models were learning what we call the latent concepts. They actually understood not just meaning of words or something, or well, let me not say understand, but they were able to extract and represent meaning, not just the meaning, but also the relationships. And that these embeddings also capture the relationships, right? And then going a step further, words were not enough. So um, these models were trained on sentences. And so now entire sentences have embeddings. So this entire sentence has a single embedding vector that contains a lot of additional stuff in it, right? The car is fast. So if you take embedding of the car is fast and calculate cosine similarity from the automobile moves quickly, you find that the difference is very small. It's cosine similarity will be close to one, right? So sentence embedding models will be able to map these two together, that kind of a similar meaning. And this became very interesting. And that spawned a lot of research that has led to what we have today, where you have large language models that actually have a deep representation. I don't want to say understanding, because understanding is the next level, but a deep representation of meaning, which is what allows them to do the magically seeming things that they can do today. Because they actually have an internal representation of the meaning, really complex meaning, not just even at the word or sentence level, but now the large language models of today can have meaning for an entire paragraph. You give an entire paragraph and it gives you a single embedding that captures the meaning of that entire paragraph, right? And can tell you whether that paragraph is happy or sad or nice. And all of those are all dimensions, right, of that single embedding vector. Those are all like it could take a feature or a combination of features and they could mean the thing. But the interesting thing is that you don't know which feature means what, right? So the tools that we currently use is to use um, similarity, um, you know, um, similarity in the, measurements or calculations, the cosine similarity, the Euclidean distance, and all of that. Okay, so this now allows sentences to be applied in a lot of things. semantic search, answering questions, clustering documents, so many things, right? And then transformers, we'll talk about transformers later when we are talking neural networks. Transformers are like the most modern architecture for neural networks that are able to do a lot of things, right? You can you can have different vectors, right? And the meaning depends on context. In traditional embeddings, you would use the same vector, right? But with transformer embeddings, different vectors. Um, Sentence A, I deposit money at the bank. Sentence B, the boat reached the river bank. Different differences. Images also have embeddings as well. You can actually take an image and put it in a convolutional neural network or a vision transformer, a VIT, and it will give you an embedding vector that tells you the meaning of that picture, what is in that image, the things that are in that image, right? So um, the interesting thing is that if you take an image um, model, embedding model, and you get an image embedding from it, right? You can use it for so many things, like a reverse image search, which is what Google uses for Google Lens to search for images that are similar. How would you be able to search for images that are similar? The way they are doing is basically of course, Google crawls the web, crawls the internet, and gathers data and catches it. So with image search, it takes images, it extracts the embeddings from each of those images as it is searching, and it stores the embeddings as well as metadata on where that image is located, the URL, and all of that. So when you now give it an image and ask it to search, what it does is the image you give to it, it extracts the embedding, and then it does a similarity search to find other images that have similar embeddings. And when it finds it, it pulls those images out. Face recognition, same thing, image retrieval. So that is kind of the summary of um, what embeddings do. So at the end of the day, when we talk about representation learning, this is what we are saying, that deep learning, and in deep learning, we are talking about neural networks, deep neural networks. We are going to go into more detail when we start, probably by next week or the week after. We'll start talking about neural networks and how all this magic is happening. But neural networks are able to learn useful representations, right? And these useful representations are able to preserve information. They're able to separate classes. They're able to identify features. And they're able to generalize well. And then you can use them for downstream tasks, right? So when you apply representation learning, what representation learning does is that it allows you to take things that are similar and group them. So this is a good example. Here, default representation, you have dogs and cats, but in the internal representation or knowledge representation of that model, it is able to create decision boundaries like this, where it is able to group things that are similar into the same clusters. This is semantic representation. But the beauty of it is that this semantic representation is now available to us through embeddings, so that we can use embeddings to extract this meaning and use the meaning to manipulate other things that the models did not even know about or did not even learn about. So I'm going to, before I just do a little bit of hands-on, I want to do a little bit of hands-on to show, um, a few things with, I've already shown one, but I want to show the similarity search and, how you can use it. Um, yeah, we looked at PCA, which is dimensionality reduction, principal component analysis, and compare it with embeddings. So in the principal component analysis, you are essentially extracting features that matter, and you are kind of extracting features in an orthogonal that are orthogonal basically. Are kind of putting it in a place where a feature is not overlapping or correlating with other features. So that if you can take the first feature or first two or three features, that tells you the importance of that feature. Right. But the main difference is that in PCA, What you have is a fixed mathematical solution. It's based on fixed maths. It's unsupervised and it has limited expressiveness. It's interpretable and it's fast. And you can use it, right? It discovers directions of maximum variance. So you get the maximum variance. If variance is a measure of the importance of a feature or the meaning of a feature, right? PCA will pull out the direction that each feature will have that maximum, and then it sorts it. So it uses the maths of matrix, um, matrix maths, eigenvectors and eigenvalues to give you that. But with learned embeddings, you are training models with data and they learn from that data the meaning of things because they have to understand the meaning for them to be able to classify complex data like images, like paragraphs or send or books, entire books. They have to learn meanings to be able to classify and differentiate. So that meaning they learn, we now make it available, right? That particular layer that contains a meaning, that's the embedding layer, which is um, a hidden layer in these models, right? And learned embeddings are often self-supervised. If you train models to be able to predict or to be able to generate the same content that you give to it, and they're highly expressive. The dimensions are large. Um, they are less interpretable. Like I say, you will not know what each of those numbers mean or what features they are pointing to, right? And of course, they're more expensive. So at the end of the day, the embeddings now form the core, the bedrock of meaning, of semantic meaning in AI of today. If you want any AI to express or exhibit intelligence, of course, that's what the I in AI means. You need to be able to deal with the semantic meaning of the input or data that you bring to it, not just keywords, not just counting the number of squares in an image or the pixels or colors, but real meaning. There are a lot of applications today. Search, we already talked about it. Image search, word search. There was a time in those days when Google search, you would have to be very careful how you type, and it will not give you things that have a different meaning. Sorry, the same meaning, but different spelling. Right? But these days, you don't even bother. You just type. In fact, of course, Google has now bumped it up to an AI mode. RAG is retrieval augmented generation. This is an AI thing. I'll look for a time to explain it. Recommend as face recognition, speech recognition, large language models, which for you to train large language models, you have to, first of all, take the words that you want to train them on and turn them into embeddings, tokenize and embed, right? And we're going to look at that in future. Vision models, the same thing. So embeddings are like the bedrock of it. And this is something that we should really understand. So the key takeaways, one, embeddings are learned representations and they represent meaning. They transform objects, concepts into vectors. And you now understand the meaning of vectors that you can decide to understand these vectors as a list of numbers or as a coordinate space in a multidimensional or a coordinate of a single point in a multidimensional space, or as a line that links the origin to that single point in a multidimensional space, which is also called a vector. So that word vector, it satisfies all the definitions of vector. And then because you have that, it now becomes easy to calculate concepts that are similar or in meaning or close together in meaning by calculating the distance between the two vectors that represent those concepts or the two embeddings that represent those concepts. You can either calculate the angular distance, which is what cosine similarity does, or you calculate the linear distance, which is what the Euclidean does, or you use a dot product. And these embeddings, deep neural networks learn them automatically in the process of you training them to do predictions and model data. So when you talk of AI of today, right, it is what we call representation learning. The models are actually learning to represent knowledge internally, right? So that's why we can easily talk about meaning. And that's why the large language models of today are as um, amazing as they are. That intelligent because they actually know the meaning. But of course, there's a difference between knowing meaning and understanding. Understanding is another level. It's only humans that can understand things. But AI, at least, they can represent the meaning of things and they can manipulate the meaning of things. If you cannot understand and manipulate meaning, you cannot exhibit intelligence. So, and embeddings are basically what has led to the success of modern AI. Transformers. Transformer is an architecture. We'll talk about that later on for modern neural networks, large language models, vision models, multimodal systems, and all of that. So I'm just going to go back and do a little bit of just to show you cosine similarity. I want to demonstrate cosine similarity. Um, so we already have shown how I use a PCA to reduce the dimensions of this embedding and plot it so you can see um, dogs are, and I would encourage you to try this, right? It's very interesting. Try different words and see how similar they look like. So the other thing you could also do, which I'll do here, is if you take the original embedding for dog and cat, then you can use similarity um, measures to calculate how close they are. So let's, for example, use cosine similarity, for example. So you can use um, sklearn matrix um, pairwise thing, import cosine similarity. So you can just, it's very easy. You just do cosine, you just call the cosine similarity. Again, the equation for cosine similarity uses dot product divided by the magnitude of each. So we can see what it gives to you. Okay, yeah, the other thing is you have to reshape the data. Cosine similarity has to take a two-dimensional matrix. So yeah, it has to be two-dimensional matrix. Actually, the first one is an n-dimensional n by the first parameter will be n by d. So the first one is n by d, where d, remember d is the embedding dimension. So in this case it's 385. While the second one has to be 1 by d. So this is the single, so this is like comparing a single word against multiple words. So what we could then do is let's take embeddings, which is all the words. In these embeddings that we had done things. And um yeah, I compare this with cat. So I already have embedding for cat, for example. So remember the first in this list of embeddings, the first one I need to reshape it to 384 by 1. So I will match the other one. So um, let me run it again. Oh, this should be reshaped, not reshaped. Okay. So this will show you the similarity. So you see, we have three values now. The first value is the similarity between the first item. So remember the first item I had dog. The embeddings are embeddings for dog, cat, and car. So just to compare so we can see. Uh, 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 So the embeddings I had was for dogs, dog close to the cat. Of course, comparing a cat with itself will give you one. That's what cosine similarity does. And then you can see the car has 0.46. So I could also compare with car. Okay. And you can see car is one and it's far from dog and cat. Now let's try something. Let's try automobile. Let me try another list. So in addition to these words here, I'll add card. I'll add care. Then I'll get the embeddings. Embeddings is model dot include words. So that'll give me all the embeddings. I'm now going to again compare with um, uh, so we'll see a new embedding for automobile. So automobile would be and then so here you can see that car again matches car, but car is far from care, interestingly. It's closer to cat, dog and cat. Now let's compare these ones using cosine similarity again. Let's compare with the automobile and we will see which one is closest. So you can see in all of this, the third one is still closest to automobile. That is 0.8, right? That's the highest value there. And that's the one that is car. But the other ones are even less. Okay. So this is the power of embeddings. Embeddings allow you to deal in the semantic domain, to deal with meanings, no more with keywords or things like that. So that brings us to the end of today's class.